Hi, my name is Omer Ozaran, and this video is for Data698 research project. His name is Predicting Hospital Readmission for Diabetes. So the project that I choose basically trying to understand hospital data and trying to predict readmission less than 30 days. Um, so for that reason, I choose the machine learning models to understand by giving the data, how can we predict the readmission less than 30 days? Is there any data information or pattern that we can understand to understand readmission rates? For the hospital readmission for patients with diabetes is important healthcare quality measure and a driver of costs. And hospitals readmission is a high priority healthcare quality measure and a target for the cost reduction, particularly within 30 days of discharge, also known as early readmission. So knowing that if with some certain condition, patient will be in readmitted less than 30 days, it's going to help the cost of the management and understanding what the next steps are should be followed by the hospital in order to prevent that readmission. For that reason, I used the University of California Irvine data sets collected from the 130 United States hospitals between 1999 to 2008. So the data that we have is it has over 100,000 the records and over 50 features, the inputs that actually can find if there's a pattern between input variables and readmission less than 30 days. For that reason, I used different machine learning methodologies such as KNN, random forest, naive Bayes, and the Mars model. And also, I use the logistic regression as benchmark model, as a baseline model, meaning that I use a logistic regression to understand by giving the data without any effort, how much can we actually see or find readmission will be. And from that point, actually, I can't say that, I have some certain amount of accuracy and then how much the rest of the machine learning models are improving the baseline or benchmark model. So for the different machine learning models, I use the KNN, random forest. They're all non-linear model, meaning that they not only they don't look at the linear relationship between input variables and the target variables. They try to find the pattern between input and the target variable with the non-linear linearity actually. Versus logical regression is going to find a linear relationship between input and the target variable. For our project, for my project, actually, I found out that linear regression is predicting 0.51 accuracy, meaning that it has a really low prediction accuracy. When I look at the different models, machine learning models such as KNN, random forest, Marsh, and naive Bayes models, among those five models, the Mars models are uh, predicting or at least giving the better accuracy rate than the remaining ones. So when I look at a KNN, it was over 0.90, which is really good, knowing that with the 90% accuracy, we will know that if the patient will be admitted in less than 30 days, and random forest is almost the same as the KNN model, and naive Bayes model actually 0.87, and I look at the Marsh models, it was 0.92, which it was the best the model in our project. Like I said, this project actually based on the hospital readmission is an episode when a patient who had been discharged from the hospital is admitted again with a specific time in 30 days. So that's why we're trying to understand here. Is that in a pattern between inputs that can explain why that patient actually readmitted, um, uh, readmitted in a hospital. Um, when I look at the different literature review, I saw that there are a lot of different um, researches that happen. The one of the research actually from the University of Michigan, they tried a different deep learning model and find out that there's some small portion of the data. They use the 7,763 records, knowing that with the limited data, having a really high accuracy is really high expectations, because once the model tries to learn from rate mission, it's not only um, dependent on the model, but also having the enough event, meaning that having the enough patient that readmitted less than 30 days. It's really a good indicator that helps the model to understand from the data. And then for that reason, that study that they did at University of Michigan, they find the most common cause for readmission was diabetes related in patient with the principal diagnosis of diabetes on an index admission, whereas the most common cause for admission in patient with secondary diagnosis of diabetes was infective related. Um, the other study that happened, this project was basically explored data research to find out the 7-day readmission risk prediction using data on patients in different level and the key laboratory markers of serious illnesses as a potential predictors of future admission for patients with a large number of repeat hospital visits. They use roughly 5,000 patients, their records. The regression model that they built actually resulted display 7-day readmission rates that were affected by age, gender, and then different condition levels. And then the model was saying that actually it's more likely that if the age goes or gender is female, the male, it's more likely the patient will be readmitted to the hospital. Um, another study, the last study that I looked at, is basically study of predicting early readmission of diabetic patient after the data preparation. They developed a decision tree and random forest classifier, which I also used it for my project on the original data set. They had it 44 different category attributes with features inputted to understand the pattern or information they can gather in order to understand why it's causing, what's causing, what's driving the patient to readmit in less than 30 days. Um, and in final phase of the study, the rule-based predictive model have been developed, and then ensuring that making sure that they have enough information from the data, and they come up with the conclusion that ensuring better healthcare for risky patients even after the discharge is important, and high-risk diabetic patients should be monitored carefully at the time of the discharge. So basically, they said that the discharge is really important, and then follow-ups for a patient actually really matters rather than age, gender, the other conditions and levels. And for project that I work on, there's some sort of order methodology that I use it. For that methodology in research project, I use the first component is uploading data. So for uploading data, as I said earlier, I use the University of California in Irvine Machine Learning Repository. The data that has it year from the 1999 to 2008. So we're having over 100,000 records and over 50 features inputs, is give me a good understanding what causing and what features are driving that readmission less than 30 days. And also I did the explanatory data analysis for my project, and that actually included showing the graphs and investigate readmission less than 30 days, and then looking at the target variable and trying to see if there's a pattern, and then how is it distributed is really important for concluding the project. And then the next one is basically investigate the readmission race input and gender versus rate mission, correlations between inputs. It's really important. I look at the different correlation metrics to see that if um, any inputs are really highly correlated, because when you have a linear model, you don't want to put the inputs are highly correlated, which also called multicollinearity test. So multicollinearity test says that if you have already one input and that's highly correlated to another input, if you put them together, you're kind of like overloading. So you're actually given another input that acts the same as the old one. So the multicollinearity is really important for regression models, and also the machine learning models that I use it. I'm not trying to overload, with that exactly the same variable, and also it causes loading up to exactly the same variable. If you have 50 variables and 30 of them, uh, and causes in the multicollinearity, meaning that they're the same thing. There's no point of putting a 30, variable in a model instead of putting just a one. And next thing that I looked at the correlation between inputs and the rate mission. That's where I'm trying to see if there's a pattern between the input variables and the target variables. And I try to investigate the patient discharge and time spent hospital. This the modeler assumptions that I made a manual assumption that actually time spent in hospital might be really important indicator why they are admitted, same as gender, same as gender and then age. For the next methodology that I use to conclude my project is data mining. For data mining process, there are some sort of encoding. There are strict values that I need to actually put in the category of the values. And I use it to different transformation functions to create a new feature in data. Knowing that one variable might not have enough information to predict what's going to happen in the next, and creating new features actually try to understand that variable in different the different version. So I use a different transformation function to understand the raw variable, and then feature imprinting, basically to fill the missing values. There are some missing values. I use a mice, the package from R for that, and then there are some missing values that, for example, gender. For a gender missing, I can't input that. I can't just tell the model just input the gender if it's missing based on what the records have been. So that I dropped it a couple columns for that reason. For feature filtering to eliminate the variables that have a great missing percentage with prediction indicators. So basically, I use the methodology, the low variance features in our packages. Basically, if the one column or one series is values are not changing frequently, that means that it's really weak prediction indicator. So there's no point in using that variable and trying to understand what's happening, especially with the large data. It's really time consuming, and you need to have really powerful machines for that. And then if I have a certain, for example, 80% are missing in a column, I chose to just drop those columns instead of inputting them. I don't think that there's going to be any additional information if the column is already 80% is missing. So next approach that I use for this project is basically to build the models. I use the different models, like I said, the logic regression, KNN models, Mars model, random forest, and then naive-based models. Our the baseline or benchmark model is logic regression, and we're challenging the logistic regression with the KNN and random forest and the Mars and the naive-based models. Once I choose and set up the models, next step that I follow is basically the model evaluation. So since I fit the model, and then I'm ready to see how they're performing. So for that reason, that I should have some sort of metric to define which models predicts the best. So for that reason, I look at the precision, recall, and accuracy and a fun score to define which models among the above is the best model in my project. For the methodology, I made a couple explanation about explanatory data analysis And then, like I said, and the data is actually imported from the University of California, Irvine. And now explanatory data analysis. Our data is imbalanced data, meaning that has a low readmission rate, less than 30 days. It's about the 6% were readmitted, whereas 94% not readmitted. So what it means for the model is basically has not enough event happen to learn why that readmission happened. So for that reason, for imbalances, it's really the problem for models to learn why an event is happening or not. So we're going to be challenging our model with that, condition actually. When I look at the 100 over 100 records in the 50 feature, there are no missing values for 43 columns, which indicated that data has a minimum missing values. And when I look at the missing percentages, there's some sort of features that actually has high missing values. When I look at the basically variable called weight, it has a 0.96, and medical specialty it has a 0.49. So 49% of the medical specialty is missing, and diabetes medication is 0.51. Payer code is 0.39. Has the most missing percentage data, and the rest of the variables have missing values that are below. And also, when we look at the graph, actually, it's showing what variables are actually have a high missing. And also the other thing that I look at the curve is for each variable. Also confirm that some sort of medications, it's called a metformin, and the other medications are highly skewed, really high values on that. And when I look at the mean values of that, they were really high. And then the graph actually shows how this the missing percentage in graphs looks like. And next thing that I look at are basically the correlation between variables. So which I'm assuming that there are some variables that actually has a highly correlated. Based on the correlation, the plot of predictive variables and between predicted and response variables above here, the top variables that positively related to targets are: one is medication change, the second one insulin, and third one maximum glycerin, which is medication, and third one is rosiglitazone medication, and the fifth one the other medication gluburide. And that also shows that there are some variables that negative correlate to admission rate less than 30 days. And the top five variable that I find out is negative correlated to the target variable is: one is age, meaning and then the second one admission type ID, and third one is discharge disposition ID, and fourth one the time in the hospital, and the fifth one number of left prosecutors. So these are the variables actually negatively correlated. And when I look at the way that readmission looks like, we can see that here. How many counts is over 100,000? We do have. I'm sorry. There are about. We can see that there are some sort of over 94,000 cases that are not readmitted, and then over 6,000 cases are readmitted. So this is what it's showing right here. Over the 6,000 are readmitted, and over the 94,000 are not readmitted. So this is a shows that actually how this is our balance, our data is imbalanced. What I'm showing here is that um, the variables, how they look, the indicate the relationship between the target and explanatory variable. I'm trying to understand if any variables that's seen here indicates the relationship between the target variable. By just looking at the here, we can see that how the relationship here, and then the above that plot is actually showing that how the some variables are looks like it. We can see that here time in a hospital, um, actually in by dates. It's how it looks like it, and then number of lab procedures, and then we can see that here how it's distributed, number of medications taken, and some sort of skewness that happening here, and then we can see that the relationship between the target and then input variables, and then I do have this graph here. So among the all 23 variables remaining after the drop in the variables, the majority of them have a clear association with the target variable, which is rate admitted. Maybe half of these predictives, if they are numerical and continuous, have a clear relationship to the target in a linear fashion. Explaining these variables from common sense perspective, they all make sense in a target rate minute. I feel that these variables are predictors that have good and continuous measurement and from that environment rather than work hard control the sources. That's why it's not surprising that they have a good linearity with the target. I guess I think the above is a good news for the predictors which favors classified model as well as the other three models. However, I have also seen that many variables, even that they are linear and numerical predictors, they either have outliers, in other words, interrupted in patterns, therefore may produce error if I fit the linear model to a outcome directly without tuning those variables or without having sophisticated modeling. So for that reason, I will be using some sort of cross validation. I'm going to be using research to find out the good relationship between the variables. Um, so when we look at the below plot, the show each predictor's box plot and then distribution, and then we can see that here for some um, you know um, for variables how they're distributed. For example, when we look at the age, I can see that here how age is mean. So basically, the patients are actually readmitted less than 30 days over 60 years old. And when you look at it on the right side, we can see that how it's actually distributed in terms of readmission rate. And then the same thing here as actually readmission type. And then I do have for discharge disposition ID. And then I do have a time and spent, and then how much time is spent, and then how it looks like it when you look at the no admission actually less than 5 days, and readmissions a little bit higher for that one. And then I'm looking at it on the right side how that distribution of the time in the hospital looks like it. And this is how it looks like it right here in density ways. And then the next one is basically readmission source ID, and I do have a number of labs procedures. And then I can see that right here in the gender. And then you can see the gender is 0, it's a female, and the 1 is a male. And then there's nothing here with the 0.5. So they basically present to 1 is a female and then 1 is a male, and then 0 is a female. And then we can see that how the females are distributed, and how the males are distributed in terms of rate missions here. Um, and also the same thing, the race, and you can see that right here. I believe I put to the different values from 0 and 1 and 2, and the 0 is white and 1 is black, and then the 2 is Hispanic, and then we can see that how which race is actually has a higher rate mission rate. So for data mining purposes, I say there are a lot of variables that that needs to be actually has a data mining. For the imbalance problem, I deal with that. I chose to drop the variables that has existing imbalance problem. There are a lot of variables that medications that actually didn't bring enough information or has a really low variances, meaning that their values are not changing enough to understand our admission rate. Um, so for the next thing that I did basically for feature encoding purposes, I used binary encoding for features, age, gender, insulin, and couple different medications here. For the next step that building a model, so for the building a model, as I said earlier, I use the different machine learning models, but for the benchmark model, I use logical regression to understand by just giving the data without any effort how much can we predict in an accuracy way. And for that reason, when I look at the logical regression, I use the 22 variables inside, and then I use the LM function in linear regression model, and then all variables I fed it directly into them model as it was defined in original data, with the missing data it's filled it in, and then some of them are dropped in basically. And then when I look at the residential residuals here, I can see that some sort of the pattern is happening, and then when I look at the F statistics, actually has a 50.73 on the 22 variables, and then has a 56,323 degree of freedom because our test trained data has 56,344 observation training data sets minus corresponding number of variables, which is 22. That's equal to 56,322 degrees of freedom here. And the next model, the few models are all assuming nonlinear fashion, which are more popular machine learning algorithms and also more truthful to do this data prediction because as we can see that linearity actually it's not that powerful to understand rate mission rate. So for that reason, I choose the sample model, I choose the decision-based model, random forest model. So for the first model, I tried basically KNN model, which stands for K number nearest neighbors, and for that actually I use it for um, tenfold for cross validation, and then 25 total algorithms, meaning that I'm not just only using what's default parameter in that KNN model, I'm using different actually parameter to find what the best parameter to understand the predictions, the rate mission rate right here. When I look at it here, I can see that here and the KNN model is predicting the 0.90 the accuracy rate, and then when I look at the true positive rate and false positive rate, and then the true negative rate actually having total is 1 here. And then the below, I'm showing that confusion matrix of statistics of KNN model. We can see that what the accuracy is happening here. And when I look at on the right side, I'm looking at how the KNN model thinks that what features are the most important. By just looking at it, we can see that here actually discharge disposition ID is the most important feature for the KNN model, versus when I look at the gender is really low, and surprisingly age is actually coming in top 5 here, and the time and the spend in hospital is really important for KNN model in order to get that accuracy highly used here. Um, and then the next plot that I'm showing you here, based on the research, how the actual accuracy is changing. It started from the 0.90 and then 0.91. It's the maximum it's getting right here. It's actually a good prediction. The next model that I tried is called Random Forest. Random Forest is one of the step further of the back tree model. Um, for that reason, um, the biggest reason that I use the random forest is because it reduces correlation among the predictors by and adding randomness to the construction process. And when I look at the accuracy rate, it's similar to KNN model. We can see that point in the last 30 digits is 0, 2, 3, and then where is this one is the 752. It's similar to the KNN model, but and also when I look at the confusion matrix, but the difference is between KNN model and the random forest is producing different the false positive rate and then true negative rates here. When I look at the feature that really important for random forest is it's similar to what we had in the KNN model. It's looking at the number lab procedures, but when I look at the race here, is actually higher ranked than the KNN model. It's here, right here, gender and race. And when you look at the gender, it's actually higher here. And then and a number of medications, number 2 here, and then time in spent in hospitals is number 3, top 3 variable that the random forest thinks is really important. And then I consider right here how the accuracy rate by the grid search and the cross validation are changing. And then the next model is a multivariate adaptive regression model, spline model. So this is the best accuracy given model for my project. And there are different assumptions that multivariate model does this. By just looking at the model actually can be overly complex by such which introduces many more unnecessary variables in addition to existing 23 variables. But that actually causes the overfitting. But I'm gonna see that I'm gonna avoid that overfitting by using the cross validation and looking at the metrics, different metrics. When I look into the accuracy rate for Mars model, I saw that it's a 0.92, which is above from logical regression, which is our benchmark model, KNN, and then random forest model. And then when I look at it here, actually, the false positive rate is 91%, which is really high. But one thing that I noticed is that basically the only variables that thinks that really high is in here number of patients. There are some small one, but I don't capture here. But it's really highly dependent on number of patients. And when I look at the different metrics here, I can see that accuracy rate how it's changing by model. It's similar to what we have in here, but this is more in density way that we can see right here. And then this is our the best models producing. And the next one is basically NIE-based machine learning that has some advantage, and then we can use that over regression model. And it uses basically a weighted effect. When I look at the NIE-based, basically it's using it's having 0.87 accuracy rate. I can see that right here when I look at the confusion matrix here. I'm having 0.83 accuracy rate, and then kappa is 0.008, and the p-values are significant level. You can see that right here, less than 0.05, which I determine as a validation point. And then when I look at the false positive rate of 0.80, and then on the true negative rate actually 0.20, so added to the 1. And when I look at the overall of 5, the summary, when I look at the over the 5 model, our model predict the various rate mission correctly, and then I have used various models such as NIE-based, random forest, KNN, and March for training our dataset, but 2 models show the greater accuracy while the remaining models do not. When I look at the March is giving the best accuracy 0.92, and the KNN and random forest is really close, which are 0.90, and the NIE base was giving the minimum accuracy, which is 0.87, which is still good, but not as good as the Mars or KNN or random forest models. For that reason, this project actually the March model is the best models that actually can understand why the patients are readmitted less than 30 days by accuracy of 0.92. And then there are some of the limitation of the data which causes actually they're not to use a deep learning. So for future work, using a deep learning model with the different layers and looking at different learning rates might help us understand the deeper relation between readmitted patient and what is driven to them readmission. Um, like I said, but actually, having really limited data might cause maybe some kind of limited accuracy, but these are really good accuracy to understand. As I said, the Mars is actually given the best accuracy rate, and I also attached here reference that I used it, and my code is actually in a GitHub, and then we can see that my GitHub here is a public, and then we can have my entire code that start from the pulling the data mining, the setting up the feature engineering, setting up the model, having accuracy for 5 models, And the other things that I wanted to try it for vector missions, but it actually needed the powerful machine. It took it over in 1 hour, and then it stopped it there. Maybe if I had a really powerful machine, I will try that one. And this is the final the conclusion for this project. And thank you so much.